orbital mechanics can defy our normal expectations of motion. And in this animation, we'll see how. But to understand how, let's first review a few things. Why we need to go into an orbit to stay in space, what mechanical energy is, and we'll also learn all about orbital maneuvers. We will then look at why, when navigating in an orbit, we need to slow down our spacecraft to move faster and speed up to go slower. First of all, what makes up an orbit? Is it just how far we are from Earth's surface? Well, if we place the SpaceX Crew Dragon capsule hundreds of kilometers above Earth with no velocity, gravity, represented by the blue arrow, will pull on it, and it will follow the trajectory of this blue line and fall out of the sky towards Earth. But if we give it some horizontal velocity, represented by the red arrow, the trajectory begins to change. And if you move fast enough horizontally, the spacecraft will never hit Earth. These high velocities that are required to achieve orbit can only be accomplished with the absence of air resistance. So therefore, the rocket has to have a high enough altitude to be out of the dense atmosphere. This speed and altitude of the spacecraft gives the spacecraft kinetic and potential energy. Kinetic energy from how fast it's going, and potential energy from how high it is, or its altitude. These two forms of energy, added together, make up mechanical energy and can be calculated through this formula. A great illustration of mechanical energy is a roller coaster. A roller coaster train will have constant mechanical energy but will continually exchange kinetic energy for potential energy and vice versa depending on where it is on the track. As it rises away from Earth, it slows down, lowering its kinetic energy but increasing its gravitational potential energy. And as it falls to Earth, the opposite is true. A perfectly circular orbit will have a constant kinetic and potential energy throughout each orbital period if the orbiting altitude is constant. But orbits are never perfectly circular, meaning they are elliptic. An elliptical orbit will have a point that is closest to its orbiting body, which is referred to as the periapsis, and a point where the orbital height is the furthest from its orbiting body, which is referred to as the apoapsis. When talking about a spacecraft orbiting Earth, these 2 points are referred to as the perigee and apogee. Manipulating the size, shape, and angle of your orbit makes up a large portion of understanding orbital mechanics. Let's briefly review different ways of manipulating orbits to ultimately understand why we need to slow down our spacecraft to go faster and speed up to go slower. The most common burns that are used are the prograde and retrograde burns. Prograde and retrograde burns are burns whose burn vectors are parallel with the direction of motion. Let's look at a specific example of each. First, the prograde burn. The prograde burn is when you fire your engines into the direction you came from. A prograde burn will increase your velocity or kinetic energy at that specific point, but not your altitude or potential energy. But as you continue in your orbit with higher kinetic energy, your inertia will cause your outward centrifugal force to be higher than that of gravity, resulting in you to slowly fall further and further from Earth as you climb in altitude. Your orbit will now be elliptic and look like this. Now let's look at that again. Your added inertia and centrifugal force is now a little stronger than before, and this causes you to resist gravity a little more, resulting in you to fall away from Earth. If we were to fire our engines in the exact opposite direction, this would be a retrograde burn, and it is very similar to a prograde burn, but in the exact opposite direction. It therefore subtracts kinetic energy from the orbit at that point of where you fired your engines, and this will affect the altitude of the opposite side of your orbit, bringing it closer to Earth. Now, if you want to increase your orbit's altitude, can't you just fire your engines at Earth instead of a prograde burn? Well, let's do it and see what happens. This burn is known as a radial out burn. A radial out burn will result in your spacecraft to resist the effects of gravity to an extent, maintaining a more straight trajectory throughout the burn. But because there's no velocity added to your orbit, as you raise your altitude from Earth, you slow down. This will pull the opposite side of your orbit towards Earth. The result is that your orbit rotates about your spacecraft with no substantial energy gain. A radial in-burn, where you fire your rockets towards space, will have the same effect but in reverse, like this. The last types of burns that can be made are the normal and anti-normal burns. The normal and anti-normal burns are perpendicular to your direction of motion. As you complete a normal burn, your rocket begins to rise up away from your initial orbit. But because you are still orbiting a planet, your orbit will slowly rotate, with the center of rotation being the planet you orbit. This change in orbit is referred to as an inclination change and is a rather fuel-costly maneuver. They are generally only used for corrections when matching the orbit of another spacecraft. Now that we've reviewed the basics of orbital mechanics, let's use what we learned to try to navigate in an orbit. Let's look at a real-life example. A SpaceX Dragon capsule rendezvousing with the ISS. Say you are in the same orbital path as the ISS, with it just in front of you. Intuitively, we'll fire our rockets behind us to go closer to it, a prograde burn. Let's see how this affects your orbit relative to the ISS. This increased kinetic energy will begin to increase the outward centrifugal force, pulling the spacecraft away from Earth faster than Earth's gravity can pull back on it. This in return causes the rocket to gain altitude or potential energy, and therefore lose kinetic energy, much like a roller coaster on the incline part of a track. This gain in potential energy results in the spacecraft to lose kinetic energy. Our new orbit now has a higher altitude and therefore a slower average speed. The Moon's orbit is a great example of this higher and slower orbit, as it takes a month to orbit the Earth. If we follow the position of our spacecraft relative to the ISS, it will rise up above the ISS and fall further behind as a result of this longer orbital period. Well, what if we do just the opposite? Let's try firing our rockets into the direction we are heading, a retrograde burn, slowing us down to see what happens. If we fire our rockets in this direction, we'll decrease our kinetic energy at that point, and our potential energy remains the same. But as we continue to orbit, the decrease in kinetic energy will result in the spacecraft being pulled to Earth faster than our inertia pulls it away. This will cause an exchange of energy from potential to kinetic energy. Now, if we follow the path of the orbit relative to the ISS, we will begin to approach it as we pass under it. This only leaves us with one problem. We are only at the correct orbit as the ISS at one point, our apoapsis. A last prograde burn is required to now circularize the orbit to replicate the orbit of the ISS. Thanks for watching, and please consider subscribing.